So the stuff that we are doing right now, or that we are starting to do right now, is not a didactic teaching. You will be like masters of your own project, responsible for your success or failure. It's not memorization and repeating after anyone, right? Okay. And since the only thing I can deliver will be some didactic things, I will keep giving some suggestions, but you are in some sense on your own. So I'll try my best with best effort, but just giving you the flavor of what is going on. So let me bring up the change. So I do not see Kennedy today in class, but if you do, like logically, we start from here. So we do have. Yeah, probably I'll start instructing how to do the project by phone, and I know that. Yeah, it will be best if you just follow what I'm showing for Coder, and then I'll suggest how to adjust the code for your own project. Okay. There's I was telling scary things that everyone is on his or her own, but it's partially true. So of course, there are some common things to follow patterns. So maybe I even need to adjust Friday meeting and do more comments on the projects, because projects are more important than didactic teaching in the class. As the biggest challenge is to set up a potential, right? So you already know how the code is working. And what I will be able to show today for sure is how to compose potential by hand without any external help. Later on, you can request help from like there are a couple of group members in my group who are like postdocs and graduate students who will happily share some input data, like data table for the potential that you can import. But if you like independence or you do not care about precise input, I'll show you what to do. Please stop me anytime, because now my goal is to help you in your projects rather than deliver specific information on my time. So if you have observed, if you have seen the code that I have sent to everyone, let me bring your attention to the line 37. So it's quite easy to run the code. I'll just show what is there. So I'm going to word. So this is just an example. One can tailor it numerically or by using some other functions, like for example, 1 divided by x squared plus w. But this equation sets up the attraction of an electron by an atom with the size of the atom controlled by parameter w. So it is very approximate, and of course all atoms are three-dimensional. And here is just one-dimensional projection of the atomic attraction of the electron. So three parameters: the depth of the potential, the position of the ion that attracts electron, and this W is atomic radius. So right now we do have this equation in the code that I did send. There is an expectation that if we place an electron with packet above this atomic stuff, even if we give some initial momentum, it will not escape the atom, but stay on the atom. So let's do this little experiment. I'm going to the method and just run the stuff that this one. So we do have the potential that I introduced, and we do have the wave function of an electron. And the electron decides that, okay, if it is so attractive here, I'm not going to leave anywhere, I'll stay here. So if you look at this distribution, it just tries to escape, but is being brought back by this attractive returning potential. I'm looking at this three-dimensional map. So please try to run it quickly, and then I'll continue the story. And I will make sure that we will arrive to the Honors project very quickly. Were you able to run it? Did you see this? Yep. Okay. I'm just going to bring up the laptop because if you allow me to point things on the whiteboard, this camera is so quite control. Okay, so one and typically molecules are composed of several atoms. So let's check how we can modify it to take several molecules. So what is the molecule, or better, I know it looks a little crazy for chemists, but solid stuff sometimes is a little easier than molecules. So if we positive ions, right, position X, potential energy, then each of the ions will attract electron this way. Okay? Then when I want to modify the X equilibrium for each atom, which will be different and add together potentials. So one needs to set up distance between atoms, and then equilibrium of the next atom will be X equilibrium plus A, X equilibrium plus 2A, X equilibrium plus N times A. So basically, we want to put us in this equation for a differential. I need to have minus A, where N is number index of an atom, A is increment distance, and here I need to have a summation over all atoms. Okay. So let's go back to method and look here. So I'm going to focus on the, instead of line 37, I'm going to focus on the lines 40 from 40 to 47. So you see there is a phrase, an equation that looks identical to what we had before. But here, instead of in addition to x minus x equilibrium, we put this minus AC times n. Then we have to make a summation over several steps. And then we are going adding this AD plus this term of each individual atom. So as we complete the solution, there will be several attractive potentials combined into one. And there's two lines with minus they will have one side of the origin, so plus will be on the other side of origin. I do have different types of patterns, steeper potential, but also technical ones. So how do I use this stuff for the actual calculation? I need to use VB in here. So I'm going to the line 56, doing comment. This is B test. 57, I will know this person. Save. And run. So you see, there's a offset of atoms, and the electron has a chance to migrate between these potentials. So this line passes by, propagates, and if you look through, it kind of chooses whatever potential is lower and where it settles. And also you see that it doesn't have enough energy to overcome this barrier. So it is trapped in a thin film of material where electron is being attracted, and it doesn't go away. So in some sense, does it run on your side? Did you try to run? Did you try to make this change and you saw this image? Okay. So in some sense, this modification of the code brings us very close to the project by Spencer. So let me check with Spencer that if there are any questions. Spencer, would you like to were you able to run this modification of the code? Okay, excellent, thank you. So I'm going to start showing what's again. I'll make a comment. Oh, no, Spencer, corner. It's a corner, right? This is a source. Yeah, Spencer, to different. Corner, do you have any questions? Not you. I will ask questions. Were you able to modify the code and do this and run the stuff that you will do right now? Excellent, excellent. So there is a source. I'm going to just mumble a few words in explaining what is the connection between things that we concluded by doing and the research on gases and sources. Box that absorbs photons generates electricity that we can use to power any of the devices. So the question is, what is inside? Solar cell. So inside this black box, there are at least two materials that need to satisfy two conditions. First, absorb, right? And second, being excited around to excite a state, they need to make a charge transfer, energy charge transfer. So why we are using the word die send source? Because dyes often absorb by weight and often makes metal-organic dyes. I'm just showing some links. And we often excites this dye ground excited. So L2 is negative. And then this material does interface an acceptor of elements. So this element that being excited, experiencing transfer from day to electron acceptor. And then, if it is connected by electrolytic circuit, then the electrons continue lack of electrons, which are move in opposite direction, and then they will combine at the device. One electron plus hole equals energy. So we can model what is inside this black box. Dye mode can be represented by one attractive potential. Later on, you can see that the levels and how to move it from the interfacing acceptor of electrons can be represented as set of attracting ions, same as in order to model this isosceles yourself, we need to first build potential that looks approximately this way. Then we need to place the initial effect at the region corresponding to the type, and then explore how efficiently it will transfer from there to the semiconductor electron acceptor. So if you're looking for a quick coursework project, one can just manipulate by potential, same as we did 15 minutes ago. If one wants to convert this stuff into true research competitive research, one may start being very careful about exact values of this potential parameters. But for the proof of concept, we could just do first shot approximate. Other, please ask any questions if you want to. Right now, you are the target client. Okay, good. So now let's go to the MATLAB and try to do this modification of the code. So this will be an electron acceptor and for electron donor for the die. We do not need so many attractive points. One to one. And we can increase the width. Just to then I'm saving this. This is the source of changes. So something is going okay, but however, do some modifications. We will do a proof of concept when we want to tailor think a little better. So the distance here we have died on the left and outline sector on the right. Or outline sector, it looks lean. For the die, I think if it is a molecule, it should be even wider. And it should stay a little bit farther away because dies absorbed to solid surfaces are connected by linkers that take space. So it is more realistic model. And we don't want something. Just remove the point for n equals 0. Better. Right now, the model has electron at the interface between these things, which is not quite realistic. So we close and more realistic situation, but I would and beginning, let's start from very slow zero kinetic energy. Okay. I'll do one more iteration for this little theory and giving more detailed comments. Okay, now it is very, very limited. So we do have excited electronic design, and if you look on the narrow, small signal, one can identify that there is a little bit deviation from zero in this line. So a small portion of the probability transfer error and happens here. Since our simulation we are using atomic units, which are very, very short time, shorter than a 10%. So if one repeats, if one increases duration of the simulation, there will be substantial part of the wave packet transfer. This model should give qualitatively correct results. We cannot hunt for quantitative, but it's already good enough. So let me check if one has some questions right now, and then I'll give a few more details. If there are questions, let me know. You may try to do these changes, or remind me at the end of the meeting to share the stuff, but you still need to make modifications yourself. No questions. Okay. Now, there is a natural question that all of you may want to ask. So what? So we have some qualitative proof of concept development, but what experiments do these observations converted into numbers? Right? If it is a charge transfer, then there are at least two questions. How much of the charge has been transferred, and how quick it has been transferred. So how can we take, how can we convert this dynamical movie in these images and answer these two questions? How much and how quick? So for the human eye on this diagram, we do not see much of the wave packet transferred to the brain. But there is a way to address it. So and this is already a program. I just need to make the introduction. So suppose that I know our probability distribution, which is wave function of certain square, has most of it here and a little bit transferred to the acceptor. Right? So we can check the definition of the segments corresponding to the segment. And then we can perform integration with the border X interface. There is 0 and there is, let's say, infinity border kind of. So one can perform integration 0 to the interface P T over dx, which means area under this curve. So this will tell us probability. We can call it like P left or P donor. Probability that electron is still in the donor. Now, for the acceptor, we can integrate from the interface to infinity or to the last edge of the box. P T dx. We can call it P right or probability of the acceptor. So these observables would give us chance to describe electron transfer quantitatively. At least it will show the amount of electron that has been transferred. So if I set up time axis and start plotting this PL then at the beginning we have everything on the donor. P left and 0 is 1. And as time passes by, it may or may not donate part of this probability to the at the same time, the probability acceptor was 0, was nothing there. But it will slowly start out with understanding that P plus left should be always 1, right? So there are some additional things called processing, but if we can generate such curves out of our computation, your hands will be untied, and you can just slam the door and go earn money by scientific activity. Stuff like this is already competitive, and you can sell it. Sell your records. So here is the image. We'll go over the code for this achievement. So we see it starts at 0 and 1, and there are 2 ones. One is growing and the other is declining. So the one that starts as 1 and declining, it is left, it is good. The one that is growing is accepted. Okay. And if human eye is not strong enough to recognize it, one can I did something wrong. There is a way to erase so let's go over the code refresh my numbers for the news of this numbers. So our probability each product time is 4 3 the results of integration that I was introducing in the PowerPoint are in the line 190. So third method, probability left, just making summation until the border. The border here is x2. Probability right, summation of this prop 3 from this border up to the end. So even if I have erased the particular, we can do it over. Oh, yes. Anyone wants to correct me? I can correct myself, but you guys can use it as well. So this P of 2 and P of the field 3 is instantaneous value. And we need to accumulate it on the trajectory. So we need to plot average accumulated. So if I plot them simultaneously, you see this pathetic image where human eye can't recognize. But if I plot only one of them, we accept. It means we are focusing on the small levels. And we need to recognize how quickly the acceptor is gaining population. So here is a tentative time for corner, but we all will follow similar procedures. So modify temperature by changing the momentum. And each time we run the dynamics, store this image and see how the amount of the charge transfer and how the rate, which is just slope of this function, will depend on the temperature. Make sense? Whether do you admit this plan, this tentative plan? Let me know if you are following and if you think you can do all these steps. Should we interpret one answer as included? If something, if you do not feel comfortable, let me know. I'm happy to give immediate comment. Yeah. But please try to do this modification of two of the things because it is actually what needs to be done for the project. Yeah, but the project for the corner is, I wouldn't say that it is basically done right now, but it is very, very close. It's already on the road. So let me pretend that I am corner. But I need help. Please reteach me how to catch the screen.
Us?
So how to like insert this image into PowerPoint?
From PowerPoint? Oh, that's funny.
You go to your PowerPoint, you go to insert, you go to screenshot. And then you go screen flipping or the window.
And here, okay, yeah, thank you. No, I am.
So just like your active screens. Yes.
All your windows, yeah.
No, equals 0. Right? Now I'm going to repeat this
I'm going to use that from now on.
experiment once again with different
I thought you had to take a screenshot first.
over here.
That was pretty impressive.
I'm using the same code and changing the P0 for a bigger value. And then I will scan it. So yes. So so do you see any changes? This is 0 momentum. And now I click on the momentum of the figure. So it looks to me that when momentum is bigger, it goes a little bit higher and further everywhere. Maybe not. The essence of the independent research that no one knows the answer except the main person who is doing research. Maybe there will be some opposite trends. But if I would be cornered, I would scan through different values of the people and record this image. And then report the trends. Of course, there are some additional things to do, but it already gives a good start. So, please interrupt me anytime. But I'm going to look at other projects and give some suggestions and general comments. Cool. Okay, yeah. So I'll be happy to help to Karen, but since she is not online, the priority is to those who attend. Jared. You need both to conduct I will give you his email. Basically, it's his first and last name. At UTC. He's very reliable and he will provide the potential that you will need to read into the MATLAB code and then basically do the same thing to we run this different initial moment. I'll talk to him and we'll discuss. Let me show you a little thing that you will need to change. So right now, in the atomic system of units, mass of electron is 1. And here, you know, the standard units, it's like 10 to the minus 30 something in kilograms, which is like ridiculous. But atomic units are intentionally designed with electron as mass 1. What is the mass of a proton? Bigger. How many times?
Like 10 times at least.
More?
More?
100 times? More?
1,000?
2,000. Okay. So if you are looking at going to chemical reaction of proton transfer, one would need to change mass from 1 to 2,000. And since things will be much slower, one would need to modify the down and hand power to go to the longer scale. If your reaction, I know for sure that this reaction involves proton transfer, but if you would do some catalysis with bigger molecules, with carbons or oxygens or groups of atoms more, then this inertia and this mass needs to be placed to a bigger value. Okay, and please do CC to me when you write to him, and I'll try to contribute during the weekend. And is it right that next Wednesday class is cancelled?
Yes.
Yes, then I need to mobilize myself and try to help you during the weekend and send something, because the program of the class will not tolerate two cancelled Wednesdays. If your schedule tells you that you need to go, it's fine, but stay as long as you enjoy it. And I'll try to focus on my projects during the Friday class, because it is a priority. The didactic class material is under control, but the projects need special attention. So, so your question, your selected research subjects are quite close. I will try to give some introductory comments, and if both you and myself have energy, I will offer a modification of your whole today. If you get tired, I just postpone it to another time. But these two projects, not theory or express, need drastic modification of the code. It's just a couple of comments. It's not much of the program I was ready to share. But there is a big idea, big philosophy behind it. So I better waste some time telling stories so that we do educated approach rather than just blindly running the code. Okay. And Marcus. first I will confuse you and myself, and then I will. So here you need to launch an imagination. You need to plot everything. So if the molecule is in the ground electronic state, we already have some orbital set orbitals. We do have some equilibrium position, and approximately potential depends on so x means interatomic distance. It's not position of electron, it's position of distance between ions, or something that describes distance between atoms. Distance atoms or direction. If we irradiate the model with light, or I'll just make it excite by radiation. Inject a charge, or just heat it up to facilitate reaction. Facilitate the reaction and change electronic state. So in all of these conditions, there is a chance that the system will go from ground electronic state to different, typically excited, but it can be just some different. I'll call it excited, but one can add specifics based on the excited electronic state. So this is a very, very common situation. So whether you excite or add additional electron, or there is a reaction that one is breaking and things are matching. The response of the potential energy on the interatomic distance will be different. So there will be different equilibrium position. Yes. Even for excited. And after you excite, interatomic distance typically expands. Sometimes it can come from average distance. There is one more parameter, typically electronic states in this equilibrium position will have different energies, which is quite natural. So if you have selected fluoronic system for mouse, your model code has to address this factor. And there is a big challenge as follows. Present version of the code does address only one potential energy source. And doesn't have transitions between different surfaces. So we need to add another surface and introduce transition between them. Let me please think about it for a minute, prepare questions if any, and I will consider, I'll try to share the code so that we probably do not waste time and do not postpone it for later. So if one is launching this this version of protocol, you do see that the thing that we were talking about, more than one connection services. And, there is a effect moves in the blue potential, and then as it approaches closer to the edge, it shrinks something into the red one. So it is like two potentials and two wavevectors. One belonging to the donor morphing state, another to the acceptor morphing state. So in the remaining two, I will try to speak a little bit more about this code that only branch, how it is different from the standard that we will consider. And basically the personal goal of Zane and Kuhn will be to identify the parameters. The potential code is there, they are parabolic, but one would need the equilibrium position for blue and red parabolas, their curvatures, and their energy offset. The values of these parameters can be, if you really want to be independent, you can just screen literature, consult with your advisor if it is related to what you do, or again, we can use help of the older compared students in the group they will be able to provide parameters. But let's watch until it is done. As you already see, it saves this thing into the form of the movie. And one of the outputs is very much analogous to the percentage of the charge transfer as we did in the previous project. Here we call it fraction yield. So it is basically how much has been transferred from product to accept. And at the initial stages it grows almost immediately. Suppose that we do not suppose that we I would think call the code is working. Suppose that we have all parameters and we just need to quickly compute the profit profile. Then we take this loop for the parameters that specify initial momentum, and we know that temperature is momentum squared to some extent. And then we rerun this code with different values of momentum, which means different temperature, and see how the slope of this reaction yield depends on the initial temperature. This, again, is a comparative research activity that one can sell in form of applications even without any experimental just by the line here. I'll cover it later, but this line is derivative, basically the slope. And since it has some numerical instabilities, it's generally positive, but it fluctuates. So in every average of this line is how quickly reaction is going on. And then after going to the top, it wants to go back. And then the reaction rate becomes negative. It's like back reaction.
So you won't stop your reaction or
I want to focus my attention on the time before it goes back. But it could be real. Sometimes it can return back to initial state. It can be artifact, but it could be also real. So I do not want to stop it at 4,000 because at the different parameters, it may go this turning point later or earlier. So I want to see the whole picture. Okay, so let's watch what is in the folder. And here is the stuff that I like the most. I don't know about. So when there is a coordinate distribution in the form of oscillates, and then it leaves a part in the acceptor, and the formula in the data is blue, the acceptor is orange. So I think it's quite good for wallpaper, in addition to the scientific. Of course, when you implement parameters that fit your interest better, the picture may look different, but general representation I think, can be used for that. And here the same thing. So origin transfer. So it grows, then after reaching about 45 up, it may turn back. But description of this initial linear regime is very healthy and interesting. So what is the main difference between this version of code and the previous one? So the PNet and the 115, just in case you need just to mass here is chosen based on the atoms that are vibrating, and it's very minor things. I'm going to show drastic change. Okay. I'm scared myself. I'm scared to start speaking about it because it is just a couple of lines, but it is very different order, different level of complexity. So, and I'll probably need just to scratch in the whole thing. So we do have two potentials. So we used red for ground, green ground, and we use blue for outside. Then Hamiltonian for the ground is kinetic energy, which is the same as plus potential for the ground. The Hamiltonian for excited is the kinetic, which is the same plus potential for outside. Make sense? Now, the thing that can be digested in a second or can just throw minus off completely. What should we do with these two Hamiltonians? It's a very probable. The situation is that depending on if we in ground or in excited, we need to use either one or another electron. How do we arrange this instantaneous swap of the operator? What will be our area of definition?
Delta.
Yes, you generally correct, but when it's more details. So here, I don't know where to start. Or maybe I'll start not from the beginning, but around the thing. Suppose we have so many grid points, 100 number of points. If we want to describe both ground and excited, and you already saw that there is a potential, there is a wave packet in ground. We need to keep track of the wave function portion that is in ground and is in the excited. So our basis for the wave function needs to be twice, 2 times bigger. Make sense? Now, in discrete representation and in numerical representation, wave function is a vector and operator is a matrix. If our wave function is twice as big, how bigger is the Hamiltonian? No. Suppose we have space, 2-dimensional space. Any vector has 2 elements. Any matrix in 2-dimensional space has 4 elements. So it's 2 by 2. Right. And if you have 4 space of 4 dimensions, right. Whew. I'm so happy. So if someone in the recordings or online has questions, ask them to Zain. So let me try to summarize. So we do need a portion of wave function for the ground, and we need a portion of the wave function for the excited. Right? Yes. And the standard way to come with it will be a vector where first part will be elements for ground, second part will be elements for the excited. The standard notation will be in Brian Kett will be as follows. Like we have a Kett for the ground electronic state multiplied by nuclear wave function. Sorry. I wanted to use right. Ground electronic state, ground wave function. Plus excited electronic state times excited nuclear. So it will be opposite. And then it will be of double dimension, twice as many elements. Now, if we want to act on this expanded size wave function by Hamiltonian, so if for ground it was n steps, for excited it was n, it will be 2n. Single Whittle Hamiltonian will be n squared. And overall Hamiltonian must be 2n squared, or 2 squared n squared. So in this logic, we are missing something. We can place Hamiltonian for Brown in this block, Hamiltonian for X in this block, but there is something missing in here, in the off diagonal element. So if you want to compose four times bigger matrix of standard matrices, we need to take something into here. We need to discuss with the logical transition. We correspond to transition from ground to excited to excited. So to the transitional Hamiltonian. I already did. This is way above undergraduate courses. If you're accepting it, you guys deserve extra credit or immediate graduation from this class. Any questions? Sound natural? Yeah. Good. So we do need additional Hamiltonian, which will be like ground excited ground. And then the Hamiltonian will be bigger. If one wants to, no, enough. Not for today, for this slide. So these ideas that we just watched in the scratching and pre-discussion needs to be implemented in program. Okay? So let's go back to the code and see. So we use third method, and here we are using. Well, I was using up and down instead of down. So we have down Hamiltonian, which is kinetic energy plus potential V2. And then nearby we have up Hamiltonian, which uses potential V1. And if you look through the error places in the code for definition, you have two parameters that you guys need to parameterize. So the only practical thing that you need to do is to find and set up parameters for these two parables, and in a systematic way modify the momentum. But nothing else. The rest is just abstract intellectual exercises. But in order to do it in an educated way, we are discussing this stuff. So in addition to this, so Hem is not food, it is Hamiltonian. Right? So Hem 3 Hem up and down. And now we have Hamiltonian up and down and down. So it has a parameter non-adiabaticity, which corresponds to rate, how intensely the electron, the quantum state can transit from between up and down. In this exercise, we do not dig deeper into the nature of how this parameter is defined. But the final result for this rate of transition will be very much different from this. And it is why Marcus got Nobel Prize. So the offset of parabolas substantially slows down the transition between electronic states. Okay, now we do have the four components of the matrix, right? And we are combining them into the supermatrix in the block diagonal block form. So up and down, down. And if I type in the command line size and 3, it tells 400 by 500. And if I do size CHEM3, 800 by 800, so it's 4 times bigger. So we kind of give it. Now, what about the wave function? Same. It also needs to be composed of the side up and upside down, right? And somewhere at the error we need to define the initial values. But the size of the wave function will be twice as big. Make sense? Okay. What else? We propagate quantum state forward in time by evolution operator, and by very good luck for all of us, and by the luck that it is quite nicely implemented in the method, we do not need to change anything with evolution operator. We just plug in into the evolution operator the Hamiltonian, no matter what it is inside. And then later on, we apply this evolution operator to wave function, no matter of what is their size. So we need to modify only the definitions. So this was how to set up the computation of predicting the future of the system, how to set up the system and how to predict its time development. Last but not least, what are our observables? What we can compare with experiment? Like reaction yield, probability that it did transfer. It is right nature. If we agreed to compose wave function as this up and down portions, if we integrate it from 0 to last point for x, it will be probability of donor. Probability of if we integrate the probability of this then it will be probability acceptor, and it will be the stuff that goes forward this time, right? So just summation of the part of the wave function. So we may want to find what it is proven and just utilize. So it should be inside the main book. So here we do have time evolution around 208, size 3 equals g tau 3 times size 3. Then we have this probability. And by the way, if we try to plot it, it will be 2 segments in different things. Later on, we need to plot them both in the same axis. So if you see it here, but we are plotting from 1 to number of points once, and then we plot second from number of points to double number of points. And then we have two images simultaneously. I would admit it is not the best abbreviation. But it is probability in the state up method 3, probability in the state down method 3. So we integrate from first to the middle, and from middle to the end. And then we do accumulated. We do accumulated in this variables a up 3 and ap down 3. So if I want to not to rely on what comes out automatically, I can redo it myself. So people, and then wording here in a p up 3. In a p down 3. So it is what we see decline of the population in the original state and increase of the population in the final state. So in some sense, by like if the parameters would be ready, then you would be ready to complete the proposal. Of course, we can look back in a skeptical and critical way and try to improve, but the core idea is here. So we go to the beginning of the code, modify the momentum, run, and record this thing. But before going into this production cycle, we need to just play and set up right run. And there, let's discuss it, but there are dedicated various students who can give some numbers. So let's do maybe last thing for today. So we need V1 and V2. Let's check whether they are defined. So that okay. Okay. So there are how many parameters? 1, 2, 3, 4, 5. And kg is not kilograms. It is spring constant for ground state. And Ke is not kinetic energy. It is spring constant for excited state. So x equilibrium is so x equilibrium for ground, x equilibrium for excited. This is d e off for their offset, and the excited to ground. So potential energy equals g x minus x equilibrium ground squared. Okay? So basically, in order to productively complete the project, we need values of this parameter. And we find where to set them up at the very beginning. And then we go forward with actual calculation. Let's check this. Spencer and Corner, are there any specific questions? So please try to repeat what we did in class. Yeah, thank you, Spencer. And the names of the various students is Around 4. There are other students that she is practically working on this only following. So it is the best source of help for Spencer. And for Zane, I think I will be okay instead of a student. Do not wait for me to express initiative, just disturb me because I'm really wanting to help, but being swamped in several things. So I believe that we came to some logical step. If you want to ask any questions or any points of discussion, I'm at your disposal. But I believe we are done with main part of today's meeting, and I think it is a success. So meeting is done. If you need to depart, please depart in peace. And see you on Friday. And looking forward to any emails that you have with us. Okay. Thank you. Thank you. Connor, do you have any specific questions? Okay. Then, if there are no protests, I'm going to disconnect for everyone.